Welcome back, guys. Today we're going to be taking a look at part B of our reciprocal functions lesson. In our first lesson, we looked at how to reciprocate a linear function, and in today's lesson, we're going to be looking at how to reciprocate a quadratic function. So before we get into today's examples, let's take a look at what we learned in our last lesson. So when we were reciprocating a linear function, the first thing we did was graph our original function. Now in the last lesson, we did that by making a table of values. And when we made our table of values, we had our x, we had our y, and then when we took the reciprocal, that affects our y values, so it became 1 over y. Now when we did that, we discovered some asymptotes. So the x-intercepts of our original function became our vertical asymptotes for the reciprocal function. And so if we plotted those points here, we would have vertical asymptotes here. So this is a linear graph, so there is only one x-intercept, and that meant there was one vertical asymptote. And that would have occurred at x equals the value of the x-intercept. Now we also learned that there is a horizontal asymptote, HA, at the point y equals 0. And so typically we would sketch those with dotted lines. Now the next thing we did was find our invariant points. And so an invariant point was where the points of the graph were identical on both the original function and the reciprocal. And those happened at y equals plus and minus 1. Because if I take the reciprocal of 1, it's just 1 over 1. When I take the reciprocal of negative 1, it's 1 over negative 1. So those points don't actually change. So on our graph, we would have plotted those invariant points. Now after that, we just have to sketch the rest of the graph. And using a table of values, that's easy because we're just plotting those points. But we did notice some patterns. All of our y values become 1 over y. And that means all of our large values of y become smaller and smaller and smaller. Because, for example, if I take a large value like 100 and I reciprocate it, I have 1 over 100. If I take an even bigger value of 1000 and I reciprocate it, it becomes 1 over 1000. And so when we take that reciprocal, we have essentially the opposite effect. Going from 100 to 1000, the numbers are getting bigger, but going from 1 over 100 to 1 over 1000, the numbers are getting smaller. And so the same thing happens when we're dealing with small values of y. Small values of y are going to get larger and larger and larger. So knowing that pattern, we can sketch the rest of the graph. Now let's take a look at today's lesson. In today's lesson, we're going to be taking the reciprocal of quadratic functions. Now, a lot of the steps are very similar. We're still going to have to graph our original function. We're still going to be finding x-intercepts. But with a quadratic function, we can have more than one x-intercept. In fact, we could have no x-intercepts. And if I have a graph that crosses the axis at two different points, so in other words, two x-intercepts, I could have two vertical asymptotes. So once I have my function, let's say my original function is y equals x squared minus 5x minus 6. If I take the reciprocal of that function, that would be 1 over x squared minus 5x minus 6. Well, if that's my reciprocal, what I'm first going to do is factor the denominator. Remember, we talk about that F word in math. The F word is factor. And so we're going to factor the denominator. Now, by doing that, we're going to find our non-permissible values, which also relate to the x-intercepts of the original function. So the x-intercepts of the original function become the NPVs, or the non-permissible values of our reciprocal function, and that means they also become our vertical asymptotes. And so these are those invisible lines that the graph is approaching. After we have our vertical asymptotes, we'll also look for our horizontal asymptote, and in this case, we will always have a horizontal asymptote at y equals 0. If you were to go into calculus or future courses, we'll look a little bit more deeply at horizontal asymptotes, but right now we're just looking at the horizontal asymptote being y equals 0. Once we have our asymptotes, then we're labeling our invariant points. And again, those invariant points happen at y equals 1 and y equals negative 1. But if we look at this graph, we actually are going to have 4 invariant points because they're happening in multiple locations. So y equals 1, we have 2 points that occur at y equals 1. We have 2 points that occur at y equals negative 1. So we would have 4 invariant points in this case. After that, we would plot the reciprocal of the vertex. So we're going to have to find our vertex, and then we plot the reciprocal. So if our vertex, or our minimum in this case, is happening at 1 comma negative 4, the reciprocal would happen at 1 comma negative 1 over 4. And then we would sketch our function, again, paying attention to the fact that as our y values are getting larger and larger and larger, our reciprocal values are getting smaller and smaller and smaller. And if the y values are getting smaller and smaller and smaller, the reciprocal values would be getting larger and larger and larger. All right, so let's take a look at some specific examples. So in our first question here, we're asked to graph the reciprocal of x squared minus 4. Now we're going to start off by plotting the original function, and then we'll use that to sketch our reciprocal function. All right, so our original function here is going to be y equals x squared minus 4. So that means we have to first find our x and our y-intercepts. You might already notice by looking at the graph that our y-intercept is happening at -4, but we can do these by plugging in 0 for y and solving for x. So if I sub in 0 for x, I'll be able to find my y-intercept. So y equals 0 squared minus 4. Basically, y becomes -4. So we already have that point plotted. Now for x-intercepts, we're going to let y equal 0. So 0 equals x squared minus 4. We're going to rearrange. So we have 4 equals x squared. And when we square root, x is going to equal plus or minus 2. So that means we're going to have x-intercepts at +2 and -2. Now, as I'm graphing this, if I want a more accurate sketch, I could use a table of values, or I could use a table of values from my calculator, but I'm just going to plot some numbers in here just to get a better idea about what that curve is going to look like. So if I take the value 3 and I substitute it into the equation, 3 squared is 9, and 9 minus 4 is 5. So I would plot that point there. And then I'm just going to erase this here so I have room. I can also do the same for -3. So -3 squared minus 4 would also be 5. Now, once we have our points plotted, then we're going to sketch the curve. Now, we'll do the best we can to try to curve that parabola. If you take a look at my notes, they'll probably be a little bit more accurate than I'll be able to get on screen. But we have kind of our parabolic shape there. Now, once we have our parabola sketched, we found our x-intercepts, our y-intercepts. I used a couple more points to try to get a more accurate graph. Then we're going to find our vertical and horizontal asymptotes. Now, we have a horizontal asymptote at y equals 0. And then our vertical asymptotes are going to happen at our x and y-intercepts. Now, if you remember, we had x and y-intercepts at plus or minus 2. So that means we're going to have vertical asymptotes at x equals -2 and x equals +2. Now, using the line tool here, I'm going to sketch in those asymptotes. So we have a vertical asymptote at x equals -2 and at x equals +2. And then again, we have a horizontal asymptote at y equals 0. So we can label those points as we go. So we have a vertical asymptote here at x equals -2, at x equals 2, and at y equals 0. The next step will be then to look for our invariant points. And if you remember, our invariant points happen when y equals 1 and y equals -1. Now, we can plug those into the reciprocal function, but often it's a lot easier to start with your original function. So we're going to start off with y equals 1. 1 equals x squared minus 4. We're going to add 4 to both sides. That gives us 5 equals x squared. And when we square root plus or minus root 5, we get x. So that means x equals plus or minus root 5, which we could put into our calculator to get a more accurate point if we needed to plot it on our graphs. We could, or not accurate, but a rounded value so that we have an idea where to plot it on the graph. Our next one will be to check, our next step will be to check y equals -1. So we're going to have -1 equals x squared minus 4. -1 plus 4 is 3. And I have 3 equals x squared. When I square root both sides, I'm going to have x equals plus or minus root 3. So I'm going to have invariant points at plus or minus root 5, comma 1, and plus or minus root 3, comma -1. And so those points can be plotted on the graph. We would have an invariant point right here. We'd have an invariant point right here, invariant point right here, and invariant point right here. Now again, my curved parabola was not drawn very neatly, and so that's going to affect my graph. When you're drawing on paper, it's important to do the very best that you can to get those points accurate. Now, the next thing we need to do is plot the reciprocal of our vertex. Now, this particular graph has the vertex right at 0, -4. What you might have to do in some cases is complete the square. to find your vertex, or use your calculator to find your vertex if you needed to. Just depends on the type of question that you have as to how difficult that might be. In this case, our vertex happens at 0, -4. So I have a vertex at 0, -4 for my original function. So the reciprocal would be at 0, -1/4. And so I'm going to plot that point. I'm still going to plot it as a red mark. Now, again, you're going to have to estimate 0, -1/4 is going to be about here. And that gives us that point. Now from there, we're going to plot and sketch the reciprocal function. So if you remember, as our y values get bigger, our 1/y values get smaller. And as our y values get smaller, our 1/y values are getting larger. So using that, we know that the graph is going to shoot up in this direction. So these values here are getting smaller. That means that my graph's going to get larger. And again, we're trying not to touch that axis. I'm going to do the best I can to sketch this out. Now the next section of graph we're looking, the graph is going to shoot up. Again, it's going to approach but not cross. And then it's going to come down here. And then we take a look at this middle section. Now, sometimes people find it easy to cover up sections of the graph and draw them as they go. Once you see that overall pattern, you'll find that they get easier and easier to graph. Now, what's happening here, this part of the graph is getting smaller and smaller, where it's approaching 0. That means the reciprocal function is going to shoot down in this direction. Again, it should not touch the asymptote. And then this section of the graph is going down as well. And then this part of the graph is going to approach that point and then approach here. Now, the bigger that, or the smaller that our vertex is, the closer this is going to get to 0, and the more squared off your graph is going to be. The closer that vertex is to 0, the more curved or less squared off that graph's going to look. So if I wanted to finish off the graph here, I could label my graph, but I have basically 3 sections now. Now let's take a look at our domain and our range for this graph. So for domain, our graph does have restrictions because we have our asymptotes at x equals -2 and x equals 2. So when I write out my domain, I'm going to have x cannot equal positive or -2, and the rest of the graph, x is the element of reals. So I'm not writing the full notation there, but we've got the gist of what our restrictions are. Now for the range, again, because our graph is in different sections, we have to consider those extra pieces. Later in this unit, we're going to talk a little bit more about piecewise functions. Right now, we're just dealing with the domain and range. Now for this function here in this middle section, I do have a maximum value. This is called a local maximum. So I have a maximum value at y is -1/4. And after that, all of my y values are getting smaller. So when I write out my range, all of my y values are less than or equal to -1/4. But if I look at the rest of the graph, all of my y values are greater than 0. So I write y is less than or equal to -4, and then I write y is greater than 0, not greater than or equal to, because it doesn't cross, and then all of those values are elements of reals. So I have those restrictions that I need to include. Now for our vertical asymptotes, we've already talked about those. We have a vertical asymptote at x equals 2 and x equals -2. You could write that as x equals plus or minus 2. Our horizontal asymptote is happening at y equals 0. And our y-intercept is happening at 0, -1/4. And then our invariant points we calculated earlier, plus or minus root 5, 1, and plus or minus root 3, -1. Now, before we move on to the next example, I'm just going to switch screens here. We're going to take a look at that function in Desmos. All right, so I have x squared minus 4. When I take the reciprocal of that function, notice those invariant points. I have an invariant point that would have been equivalent to -root 3, and then I have another invariant point here, and my invariant points at 1 and at +1 here. And notice this point here, the maximum value right there would be happening at negative or 0 and -0.25 versus here where the minimum point was 0 and -4. Now taking a look at example 2, this is very similar to the first example of x squared minus 9. So what I'm going to encourage you to do is pause the video, do the question on your own, and then come back and check to see if what we have matches. Okay, taking a look at example number 2, the first thing we find is our x-intercepts. We sub in y for, or 0 for y, and we solve for x. So we have x equals plus or minus 3. That then becomes our vertical asymptote. So we have a vertical asymptote at x equals negative 3 and x equals positive 3. And then our y-intercept, we would sub in 0 for x and solve for y. We have a y-intercept at negative 9. Now that didn't quite fit on the chart, so I just graphed it a little bit below, added a few extra lines. So we have y equals negative 9. After we have our vertical and horizontal asymptotes, remember we also have a horizontal asymptote at y equals 0, then we look for our invariant points. And so our invariant points happen at 1 and negative 1. So we sub those in and solve for x, and we have an invariant point at plus or minus root 10, and then another one at plus or minus 2 root 2. So the square root of 8 becomes 2 root 2 when we simplify. We plot those points on, so I put those in red. We've got invariant points at these 4 places. And then we have to look at our vertex. So the vertex of the original function happened at 0, negative 9. So the reciprocal of that would be 0 and negative 1 over 9. Now again, this was a fairly easy one to see. We didn't have to worry about completing the square, but we'll go over another one of those examples shortly. Once we have our graph plotted, then we're looking at our domain and range and asymptotes and so on. So this is kind of where we're summarizing everything for the function. Now, our domain, we have those restrictions of plus or minus 3. So our domain would happen at x cannot equal plus or minus 3. The rest of the graph would be x is the element of reals. For our range, we have to consider both pieces. So we have this point here. It's a local maximum at negative 1/9. So all of my y values are less than or equal to negative 1/9, but all of my y values are greater than 0 as well. And then y is the element of reals. Our vertical asymptotes happen at x equals plus or minus 3. Our horizontal asymptote happens at y equals 0. Our y-intercept happens at 0, negative 1 over 9. And then our invariant points are at plus or minus root 10, 1 and plus or minus 2 root 2, negative 1. Now we're going to take a look at one example that is not in your notes, and that's just because we haven't seen one where the vertex is not necessarily as obvious. Now, in this particular graph, our vertex will still be obvious, but I'm going to show you how we can check for it algebraically. So if I'm given this function here, I'm told that the equation is x squared minus 2x minus 3. A lot of the graph can be figured out just by looking at our function as it's graphed. So our vertical asymptotes happen at our x-intercepts. So remember, our reciprocal function would look like 1 over x squared minus 2x minus 3. So if I want to figure out where those asymptotes are going to occur, I got to take and find my NPVs, and that I'll do first by factoring. So x squared minus 2x minus 3 becomes x minus 3 and x plus 1. And that means our asymptotes are happening at x equals 3 and x equals negative 1. We can see that from the graph as well, but I'm going to sketch those lines in. So we plot a point at x equals negative 1, or we plot a line at x equals negative 1 and at x equals positive 3. So those are our vertical asymptotes. And then again, we would have a horizontal asymptote at y equals 0. So we can mark all of those lines. We have x equals negative 1. We have x equals 3. And we have y equals 0. So while I'm saying here these are restrictions, x can't be 3 and x can't be negative 1, we're writing our equations as x equals. And again, we have a horizontal asymptote at y equals 0. Now, to find our invariant points, we're going to sub in the values of 1 and negative 1. So we have 1 equals x squared minus 2x minus 3. We rearrange our equation. We're going to have 0 equals x squared minus 2x minus 4. And then to find our values, the easiest way to go about doing that if this is not factorable is to use our quadratic formula. So we're going to have negative 2, so a positive 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 4. And that's all divided by 2a, which is 2 times 1, which is positive 2. Now simplifying that down, we're going to have 2 plus or minus the square root of 4 plus 16, so the square root of 20 divided by 2. And when I rearrange, remember that with 20, we can break that down by pulling out a square root 4 and a square root 5. So we have 2 plus or minus 2 times the square root of 5, all divided by 2. And then this will simplify down. So we're going to have 1, 1, and 1. So our point here would become 1 plus or minus root 5. So our invariant point is going to happen at 1 plus or minus root 5, comma 1. And then we would have to do the same for negative 1. And with the magic of video editing, you can see that our other invariant points are going to happen at 1 plus or minus the square root of 3, comma negative 1. Now we also need to find our vertex. If we take a look at the vertex here, it's happening at 1 comma negative 4. But if we didn't know that, we could find it by using completing the square. So we're going to have our original function of y equals x squared minus 2x minus 3. And then to complete the square, we're going to section off those first two terms. And we're going to have y equals x squared minus 2x in brackets minus 3. We'll do half squared, so y equals x squared minus 2x. Half of 2 is 1, so plus 1 minus 3. And then y equals x squared minus 2x plus 1. Pull out the negative 1. Now remember, if this was a function that had a coefficient in front of the x squared, we would have to remember to multiply it by that number. And then we factor. So we're going to have x minus 1 squared minus 4. So our vertex is happening at positive 1, comma negative 4, meaning our new vertex is happening at positive 1 and negative 1 over 4. And so we can plot that point 1 and negative 1 over 4. And we mark our invariant points, which are happening here and here. So the only reason we would have to have the exact values is if you're asked for the exact invariant points, and that's where you may have to use the quadratic formula. Once we have that, then we can sketch our diagram. So it's going to curve up to that maximum value, curve down, and then come straight down, and come straight down. And again, as our values are getting smaller, our 1 over y values are getting larger, and this part of the graph is going to shoot up here. And the graph will be similar over here. So again, we have those three sections. Now taking a look at our next example here, we're given the reciprocal function of y equals 1 over f of x, and we're asked to find the original function. And so we're going to look for some of those key points starting off. Our asymptote is happening at x equals negative 2, so we know that the x-intercept of the original function will be at negative 2 comma 0. We can also find some invariant points. We have an invariant point here at negative 1 comma 1, and we have an invariant point at negative 3 comma negative 1. Now, if you remember this, looking at it, we know is going to be a linear function. And so what we have to do is find the equation of that linear function. So going back, we're looking for y equals mx plus b. And to find our slope, we need to first use our slope formula. So we can pick any 2 points. I'm going to choose the negative 2 comma 0 and the negative 1 comma 1. So starting off, I'm going to find my slope, which is m. M equals y2 minus y1 divided by x2 minus x1. And that's going to be 1 minus 0 divided by negative 1 minus negative 2. Remember, when you're working with the slope formula, it might be helpful to label your points, x1, y1, and x2, y2. And so 1 minus 0 is 1, and negative 1 minus a negative 2 is a positive 1, so I have a slope of 1. Then I have to find my y-intercept, and so that's my b value, and I can do that a couple different ways. One is to use my slope formula. We can also use the point slope form. I won't get into that right now, but we can sub in 0 for y. So we're taking one of those coordinates. I've chosen to use the 0 and the negative 2. I'm going to sub in 0 for y, 1 for the slope, and negative 2 for the x value to solve for b. So I have 0 equals negative 2 plus b, meaning that b equals a positive 2. Once I have my slope and my y-intercept, I can graph that function. Okay. Again, remember your calculator makes a really good straight edge. And so I'd sketch that graph. Now, if I'm asked to give the equation of that line, I would use my slope and my y-intercept. So the equation of this line would be y equals 1x, or x plus 2. So taking a look at example 4, again, we're given a reciprocal function and we're asked to find the original function. So we're going to start off by looking at the points that we know. First of all, we have our asymptotes. So we know that we have an x-intercept at -2 and an x-intercept at +2. Based on the shape of the graph, we know that we're going to be looking at a quadratic function. We can also take a look at our vertex, and our vertex looks to be happening at about 1/4. Okay. And so I can plot all of those points here, write them down. We know that we have a point here at -2, 0, another point at 2, 0. We can also look at our invariant points. We have invariant points at -1 and +1, and so those would be happening in those points located. Now, our vertex here is happening at 0, 1/4. So that would tell us that our original vertex would have happened at 0 and 4. Now, while we don't know the specific points for those invariant points, it will still help us with graphing our function later. We want to actually find the equation of the function. So we're going to use the vertex form of the quadratic formula, which is y equals a times x minus p squared plus q. And we sub in what we know. I'm going to choose to use the point 2, 0 for solving this equation. So I'm going to use that as my x and my y, and then 0, 4 is going to be the p and the q. So substituting in, we have 0 equals a, which is what we're looking for, 2 minus 0 squared plus 4. And simplifying, we're going to have 2 minus 0 is 2, 2 squared is 4, so we have 4a plus 4. Subtract 4 from both sides, we have -4 equals 4a. Divide by 4 on both sides, and we have a equals -1. So using that, we can write our equation as y equals -1 times x minus 0 squared plus 4, which simplifies to y equals -x squared plus 4. Using that information, we can then sketch our original function. And so I'm going to just mark those invariant points in red. We know that those points are going to stay exactly the same. We also know that our new vertex is going to be at 0, 4, and then we can sketch our graph. So the graph is going to be opening down. It's going to go through our go through our x-intercepts and then continue on down. So this may not be a perfect sketch, but as long as all of those key points are covered. Now, moving on to example number 5, we're again given a reciprocal function and asked for the original function. So the first thing we're going to do is look for some key points. We have asymptotes at x equals -3 and x equals +4. So we can write those down, x equals -3 and x equals +4. We can use those to find the factors, or our x-intercepts, which turn into factors for our original function. So if our x-intercepts are happening at -3 and +4 for the original function, that means my factors would be x plus 3 and x minus 4. And so I can expand that out, and that gives me x squared minus x minus 12 equals 0. Now we don't know exactly how wide this graph is, so this would be the same as writing y equals a times x plus 3 times x minus 4. Now we're going to, for the purposes of this, assume that our original function is y equals x squared minus x minus 12. Now, in order to plot this, we're going to have to figure out where our minimum value is. And so we can also do that by using our calculator. And so we can use the completing of the square. We can also use our calculator. So I'm going to type in y equals x squared minus x minus 12. And I'm going to graph that on my calculator. Now it goes a little bit below, so I'm just going to zoom out a bit on my graph. And I can find my minimum. So second calc minimum, go a little bit to the left of the minimum, a little bit to the right of the minimum, enter, And we have our minimum happening at 0.5 and negative 12.25. So our vertex, so we want to write in there, so we did second calc and then we did minimum. Our vertex was happening at 0.5 and negative 12.25. So that's what we could plot as our minimum value. And our y-intercept would be when x equals 0. So we can sub in 0, we would have 0 plus 3, which is 3, times 0 minus 4, which is negative 4. And so we end up with 3 times negative 4, which is negative 12. So we're going to have a y-intercept at negative 12 and a minimum at negative 12.25. Now, when we go to sketch this graph, it actually is going to go well below our points that are shown on the graph. So I'm just going to extend the graph a little bit here. So this is going negative 5, and then we'd have 6, 7, 8, 9, 10, 11, 12. And so our vertex is going to happen, or our y-intercept is going to happen at 0, negative 12. And we know that our vertex goes slightly below that at about 0.5. It's going to be at negative 12.25. We also have invariant points at 1, or at y equals negative 1. We're going to have invariant points at y equals 1. And so we can sketch our graph from there. Now again, trying to sketch those points, you're going to do the best you can to line everything up. We're going to come down, go through the y-intercept, through the minimum, and then we're going to come back up through those other points and try to curve it as smoothly as you can, do the best that you can. Again, paper's a little bit easier than trying to do it on screen, and our graph is going to go up in this direction. And so there we would have our reciprocal function and the original function. All right, that's our last example for today. So hopefully that's given you enough information to get started with reciprocal functions for quadratics. If you have any questions, remember that I'm always available to ask questions in tag or class. All right, guys, have a great day and we'll see you soon.